Because of this, renewable technologies that are economically competitive and have a smaller ecological footprint are gaining market share and public support.
We are also now in a world that is very focused on carbon, very concerned about climate change.
Energy and climate change are really synonymous. We don't have much in the state itself in terms of producing CO2 from our energy sources, since we're mainly tied to Hydro-Quebec and Vermont Yankee. But the system of New England that we're all part of, there are a number of plants that are either burning coal or oil.
Over the past hundreds of years, human society has gone through several energy transitions. We've made shifts from wood to coal, coal to oil, and now increasingly oil to natural gas. Driven in large part by climate change, electricity producers are now looking to shift to renewables. Large-scale hydroelectric plants and wind farms are the most economically competitive renewables, but advances in solar technology are driving down its price and increasing investment. Concentrated solar thermal technology uses lenses and mirrors to focus the sun's energy, producing heat. Tubes filled with a thermal conductor, typically in oil, are heated to very high temperatures. This is used to generate steam, which, like nuclear and coal, turns a turbine generating electricity for the grid. In contrast to solar thermal, traditional solar photovoltaics generate a current when sunlight excites electrons in a silicon membrane.
The other is the whole emerging economy on biofuels and what type of feedstocks are we going to use. Or even more promising in the near future is the use of algae to create a biofuel. There's a lot of things that are happening as far as the science in this area.
More and more people are realizing that local actions have global implications. Our choice to burn coal or use nuclear has real consequences for the health of the planet. In an effort to move toward more sustainable sources of electricity, Vermont scientists are investigating the viability of renewables and finding significant business opportunities in doing so. Julie Marble, CEO of Sentient Corporation, explains how they are transitioning their proven success in modeling failure rates of helicopter rotors to predicting failure rates of wind turbines.
We are known as the bearing guys. What we do is predict more accurately than anyone else when critical components are going to fail. The reason that Sentient is in business, there are 2,900 Black Hawk helicopters in the United States. What Sentient does is create a system based on physics models of how bearings fail and automatically provides an expert system, a computer program, that can say there is a fault at this point. Right now, Sentient Corporation is leveraging the work that we've done for the Department of Defense into wind energy. We focus on bearings and gearboxes. A bearing consists of the inner race, on which are laid a number of rotating components. So we can predict accurately whether this bearing has 700 hours left or if it has 70 hours. Our EPSCoR grant is about, and what our DOE Phase 2 is about, taking the data that can be gathered off of a wind turbine, analyzing that data, and predict when critical components are going to fail. The Department of Energy has a plan to promote 20% of the U.S.'s energy to come from wind by, I think it's 2012. In the next 4 years, there's a $400 billion market for wind energy. If you understand the physics of how these systems fail and how they run healthfully, then you can extend the life of those systems. You don't have to replace them, and you provide energy long-term.
Like Julie Marble, other Vermont scientists are finding opportunities in the rapidly growing wind industry. John LaRue is harnessing his expertise in optics to make wind turbines invisible.
I started thinking about the problem of things being visible and people not liking things visible, but they like the things in terms of the broadcast towers, the cell phone towers, and so on. Especially in a place like Vermont, you don't want the wind generator on top of a mountain, but that's most of the time the right place for it. The concept begins with the same concept as the optical fibers that's used to make the World Wide Web, part of the physical aspect of the internet that carries your little jokes all around the world. The idea that we have here is that we use the light from the background sky and try to bring that light and transmit that around the object. It's done by light that's captured inside of a piece of clear material. And the idea is you put a coating on here where the light that strikes this side of the object will be transmitted around the object and later on make it so that it is expelled, emitted. There are really three questions. What causes the light to be captured that comes here? What causes it to continue to be transmitted around the object? And what causes it to get off the boat, if you will, as it goes around? You have this optical fiber, two-dimensional thing that you coat on here that covers the whole object so that any light, any place along here is contained within that and is transmitted all around it. You put an irregularity in there, something to change the direction of the light at some particular point. It becomes, in that sense, a light management question. What you typically want it to be is less visible to people that are looking at it from the north side or the south side or the east side or the west side. In order to do this, what you need is something that dynamically, continuously reflects the sky background.
The individual wind turbine presents its own set of challenges. As we start to explore large-scale wind farms, integrating wind power into the existing grid becomes the paramount issue. Paul Hines, another EPSCoR-funded scientist, is grappling with how to integrate power from new and intermittent sources.
There's a lot of interest right now in introducing renewables into the electricity grid. And wind power in particular has at least potential to be a cost-affordable alternative to fossil fuel sources. One of the tricky parts with wind, unlike the fossil fuel or hydro resource where you can turn it on and off whenever you want it, the wind kind of blows when it wants to. What we're studying here is trying to figure out, as the wind goes up and down and as it fluctuates, how do we integrate that new energy resource into the existing electric power grid? What is the cost of integrating that fluctuating resource into the power grid? We have to produce electricity and consume electricity at exactly the same rate at every moment. And so when I flip on a light switch, some power plant has to generate a little more electricity to meet my additional demand. The grid is an interconnection of transmission lines connected with one another so that any electricity that you stick in at one point can be delivered to any point within that grid. It's a nice infrastructure in that you can generate electricity basically anywhere and deliver it to any other location. The grid really includes a lot of different components. It's not just the power lines or the generators. Human operators that sit behind desks and monitor the status of the power grid, trying to make sure that generators turn on and off at the right times. There are markets, power exchanges where people are constantly trading electricity financially. And so all these things are interconnected. Sometimes we think of them as agents. So you have human agents and generators that are sort of mechanical agents, and they're all working together to produce electric energy. And it's kind of miraculous that it works as well as it does, actually. In our research, we're trying to model all these pieces together instead of looking at each one separately, and seeing if these pieces together tell us things that we wouldn't see if we looked at any one piece very myopically.
As it turns out, developing renewable technologies is not enough. Scientists now realize that the transmission infrastructure itself has to evolve. One idea that harkens back to Edison is that power comes not from centralized sources, but from decentralized locations in communities. Neighborhoods generate their own power, municipalities put up wind farms, and electricity produced from these appropriately scaled generators contribute to a smart grid, where consumers intelligently control power.
Well, the way that we've structured this traditionally is to build very large generating power plants and put them away from where the people live, and then stick the electricity into the power grid and then deliver it to other locations.
Distributed power is building the source of your electricity or power close to where you're going to use it.
There's a lot of interest in returning to the days of Edison, where the power plant was right next to where the people live. And so this idea of a microgrid or distributed generation is an increasingly popular idea.
From our perspective, before you do big wind, you should do little wind. You know, before you do big solar, you should do little solar. And when you exhaust your capacity to extract useful work from the sunlight that falls on your buildings and falls in your backyard and falls in your parking lots and the like, you know, then go out from there. I have been an advisor or a consultant to the energy agencies of Presidents Ford and Carter and Clinton and George W. Bush. So I've sort of been on the inside and been on the outside, you know, watching the developments occur. For me, energy independence starts from the bottom up. And otherwise, I don't think that you can get to where I want to go. Technology moves on, and what we are learning is how to extract more useful work from slower and slower moving molecules, if I could put it that way. And so if you have a small stream, we now can generate electricity from it. We don't need a raging river, and we don't need a dam. So, you know, my feeling is that, you know, energy, you know, that if you're talking about sustainable energy, you're talking about renewable energy. If you're talking about renewable energy, you're talking about energy that's available almost everywhere, although in varying amounts. And that's what you should tap into. And when you exhaust your ingenuity there, then you move into more remote renewables, or, if you have to, more remote fossil fuels.
Energy, and certainly electricity, is the currency of human economies. Because our choices of energy are so critical to mitigating and ultimately adapting to a warming world, low and zero carbon technologies will be the wave of the future. Energy transitions in the past did not occur because we ran out of resources, but because we came up with a better alternative. I'm Amy Seidel. Join me next time for more emerging science.